Luke said, I'm Joshua. I'm going to talk about a counterexample to the reconstruction conjecture for locally finite trees. And what I'm going to be talking about today is joint work with Nathan Bowler, our first speaker today, Peter Heinig, Florian Lehner, and Max Pitts. Okay, so in its broadest sense, a reconstruction problem asks whether we can identify a certain structure just by the information that is contained in some collection of its substructures. And so for the talk today, the structures we're going to be thinking about are going to be graphs, infinite graphs, and the substructures from which we're going to try and reconstruct them are going to be the vertex-deleted subgraphs. So I'll give a little example of a finite graph to show what we're talking about. So here's a graph, and we could pick a vertex in the graph, and then the vertex-deleted subgraph is what we get when we delete the vertex. And so here we have this subgraph arising from that vertex. And so this graph is going to have many different vertices, and they each will have a vertex-deleted subgraph, although we might get the same graph from different vertices here. And we're going to remember how many times each graph comes, even if we get the same graph. And so if we run through all the vertices, we're going to end up with this collection of vertex-deleted subgraphs, and the original graph there on the left. But we can ask, well, what if we forget about the original graph, and we were just presented with this collection of subgraphs? Can we work out which graph it came from in the beginning? And this is really the idea behind the reconstruction conjecture. Okay, so just some notation so that we're all on the same page when I talk about certain things. If we have a graph and you take a vertex in the graph, we're going to call the card of V, the vertex, is just going to be this graph we get when we delete it, the vertex-deleted subgraph. And the deck of G is going to be the multiset given by all the cards. And so we say a graph G is reconstructible if there is no other graph with the same deck. It's the unique graph that has its deck. Okay, and so perhaps a very natural question to ask, given these definitions, is, well, which graphs are reconstructible? So very small examples, both of the graphs on two vertices happen to not be reconstructible because they have the same deck. But it's conjectured, and it's a very old and famous conjecture, I think attributed normally to Kelly and Ulam, that every finite graph on at least 3 vertices is reconstructible. And this is known as the reconstruction conjecture. And so if you spend enough time in Hamburg, perhaps you might ask, well, why do we only care about finite graphs? And especially at the time when this was first considered, infinite graphs were perhaps considered on more of an even footing with finite graphs. And so not long afterwards, the question was asked, I think formally first by Harari, is every infinite graph reconstructible? So sadly, it turns out that this isn't the case. And Fisher, Graham, and Harari gave an example, a particularly simple example, of a countable tree which is not reconstructible. And it's so simple that I'll show you the example here. So this here is a tree which is regular. Every vertex has the same degree, and every vertex is going to have countable degree. So here each vertex has countably many neighbors coming out. So because this tree is regular, it's going to be vertex transitive. So every vertex looks like every other vertex. And so the deck of this graph will consist of the same card counted many times. Each vertex will have the same card. And so if we consider an arbitrary vertex, say this one at the bottom, what will its card be? So if we delete the edges adjacent to it and the vertex, the tree is going to split in countably many components. And each of these components is going to be isomorphic to the original tree itself. So the deck of this graph is just countably many cards, each of which is a countable union of disjoint components, each of which component is the original graph, which is quite a mouthful. And so what Fisher, Graham, and Harari noticed is that if we considered, instead of just the tree, the graph which is composed of a disjoint union of 2 copies of this tree, the same thing will be true. If we remove a vertex from either copy of this tree T infinity, that copy will split into countably many disjoint copies, and this extra one here really won't make much difference to the isomorphism type. Okay, so that's rather sad. The reconstruction conjecture isn't true for infinite graphs, but this counterexample is pathological for maybe a few reasons. So firstly, maybe it's not very nice that one of the graphs is connected and the other is disconnected. And we might ask, well, maybe we can reconstruct graphs from within the class of connected graphs. And the second reason is perhaps more interesting, is that this graph has vertices of infinite degree. And so we say a graph is locally finite if every vertex has finite degree. And Nathan talked about these graphs earlier, and in many ways these graphs behave a lot more like finite graphs than arbitrary infinite graphs, which can be very pathological. And so it was conjectured that in fact the reconstruction conjecture should be true for locally finite trees, and in particular locally finite graphs, and in particular the most simple locally finite graphs, which are locally finite trees. And this is a conjecture of Harari, Schwenk, and Scott. So I should mention that the reconstruction conjecture was known to be true for trees, and already when this was conjectured, and that was proved by Kelly. So there was actually a lot of work done towards proving this conjecture in the next sort of decade or so. And so initially, Bondi and Heminger showed that every locally finite tree with finitely many, but at least two ends is reconstructible. And so an end is this thing that Nathan was talking about earlier. An end, well, I won't go into the exact definition because it's not going to be useful for us, but in some way it's a point at infinity at the graph. And having two different ends means there's two different ways to go off to infinity in the tree. So this theorem was improved, firstly by Thomason, who showed that actually also locally finite trees with one end are reconstructible. And then also Andrea eventually showed that every locally finite tree that has countably many ends is reconstructible. And so altogether, this almost covers all the cases. So it can be shown that a locally finite graph has either countably many ends or continuum many ends. And so together, these three theorems cover all of the countable cases. And so all that's left is to show, would be to show that every locally finite tree with continuum many ends was reconstructible. But sadly, this wasn't shown in the next 30 years or so, and eventually our main result was we were able to show that, in fact, the reconstruction conjecture is not true even for locally finite trees. And in fact, we even showed that it wasn't true for trees with a bounded maximum degree. And in fact, our bound here was very low, it was 3. So we were able to build a pair of non-reconstructible trees of maximum degree 3. And so hopefully I should have time to go through really the main points of the construction here and sort of explain to you how we did it. So, given two graphs, T and S, we're going to say that a vertex X in T and a vertex Y in S, they're paired if they have the same deck in their card in their respective graphs. So if T minus X is isomorphic to S minus Y. So what is it that we want to build to find a counterexample to the reconstruction conjecture? We want to find two locally finite trees, T, which is not isomorphic to S, but such that there is a bijection between the vertices, so that the corresponding vertices of T and the vertices of S, so that the corresponding vertices are paired in this way. And then that will guarantee that the two graphs have the same deck. And so the way we're going to try and do this is going to be via a back and forth construction. So it might be difficult to see how we could guarantee that we have this pairing between the vertices all at once, but maybe we could try and pair individual vertices one by one at a time, and go through all of the vertices in these two trees and maybe hopefully pair them off eventually. So we're going to start with two trees, T naught and S naught, just that are non-isomorphic. And so we're not going to say that there's any pairing going on. And so suppose we have a vertex x1, which is in T naught, and we want to find a pair for it in S naught. So there's no reason this should exist, right? These are arbitrary trees. There probably isn't a vertex y1 in S naught that is paired with x1. So maybe, rather than try and find a pair for it, maybe we can extend the graph slightly. So we build some super trees, T1 of T naught and S1 of S naught, such that there is a pair for x1 inside this bigger tree. So now we build T1, and hopefully we can build it so that it's still not isomorphic to S1. But now x1 is paired to y1 in this tree here. And so this is sort of the fourth part of the back and forth construction. And so we could maybe try and deal with all the vertices that lay in T naught and T1 and eventually doing this. But in the back stage, we're going to deal with the vertices that lie on this side in S. So now suppose we have a vertex y2, which lies in S naught or S1. We'd like to say that there's a pair for y2 in this half of the diagram. But again, there's no reason one should exist in what we have already. So maybe we need to make the graph slightly bigger again. So maybe we extend T1 to a graph T2 and S1 to a graph S2, again, hopefully such that they're non-isomorphic, and hopefully such that there is a pair, X2 now for Y2. But we already had this pair, X1 and Y1, and we don't want to ruin that when we extend these graphs here. So we're going to hopefully be able to do it in such a way that X1 and Y1 are still paired in these bigger graphs. And this here is really the meat of the proof. I'm trying to find a way where we can do these extensions and maintain our old pairings. And so I'm going to assume that we know how to do this and talk about how the rest of the proof will go, and then we'll come back to this step later and sort of talk in more detail about how one might do that. So supposing we could keep doing this sort of step, picking a vertex in T, finding a pair for it in a slightly bigger graph over here. We could maybe go through all the vertices in both of these things in order in some countable sequence. So even though we're adding vertices at each step, as long as we only add countably many, we can make sure if we do this countably often, we deal with every vertex eventually. So eventually we'd end up with some sequence of graphs, T0 contained in T1, contained in T2, and S0 contained in S1, contained in S2, and some sequence of vertices, xi and yi, that we'd paired off in each of these stages. And so we'd end up with such graphs, such that if we considered, say, the 10th thing in this sequence, T10 and S10, then x1 to x9 would be paired with y1 to y9 in T10. We can sort of think of this as sort of building sort of larger and larger sets which we pair together inside these eventual graphs we're going to build. And so perhaps a good thing to take as our eventual trees is going to be some sort of limit of these sequences here. And so what we're going to do, I might have to draw something here. So if you have a sequence of graphs, sort of increasing sequence like this, there's perhaps a natural object to consider as the limit, which is just to take the vertex set to be the union of all the vertices. And for any pair of vertices, they're going to appear in one of these subgraphs, and we take an edge between them if there is an edge in the subgraph in which they first appear there. And so you can just think of this as drawing T0 and then drawing T1, then drawing T2, and sort of as they go out. And S similarly. So we're going to define these graphs T as a union of the TIs and S as a union of the SIs. And we're going to hope that these can be our counterexample to the reconstruction conjecture. So firstly, we should hope that these things have the same deck. So definitely we've got this big collection of vertices, this xi's and these y's here. And we might think that if we were careful about how these isomorphisms extended from the stage n to the stage n take 1, that this might still hold true in the limit. And indeed, we will be able to make sure that happens. And so for every xi and yi, xi is going to be paired to yi in T and S. But we might not be done because this might not be all the vertices. And so this is sort of what I was talking about earlier. So we were going to need to be careful in the way that we pick these sequences of xi and yi so that we actually use all of the vertices in T and S. But again, it's not too hard to make sure that happens. And then finally, in our construction, we're going to make sure that T0 isn't isomorphic to S0 and T1 isn't isomorphic to S1 and so on. And again, that's not quite sufficient to show that T isn't isomorphic to S, but the details in how we show that aren't especially interesting. It's not too hard to use our construction to make sure these objects at the end here are not isomorphic. So the main problem that we need to get by is how do we actually do this this inductive step of going from Tn to Tn plus 1 in such a way that we can maintain these pairings that we have already. So I'm going to sort of write out explicitly what it is we're going to need to show, just so we're all on the same page. So in an arbitrary step, we have two trees, Tn and Sn, and we have some sets, x1 to xn take 1 and y1 to yn take 1, such that these vertices are paired in these two graphs. And we're going to pick some arbitrary xn, which lies in Tn, and then we need to build our next step, our next stage of our graph. So a Tn plus 1, which is a supertree of Tn, and an Sn plus 1, which is a supertree of Sn, such that, well, they're still not isomorphic. There should be a yn in Sn plus 1, which is paired to xn, and also all these pairings we had from the last stage still hold in the next stage. And so the question is, how can we extend this whilst preserving these pairings? And so the idea is going to be that we're going to try and use a slightly stronger induction statement on these Tn and Sn. So what we're going to assume is that we've got some sets of leaves, and we're going to color these leaves red and blue, and we're going to assume that each of these isomorphisms that showed that xi was paired to yi preserves the color of the leaves. So that is to say, Tn minus xi is isomorphic to Sn minus yi. That was the definition of being paired. And we're going to ask that these isomorphisms send red edges to red edges and blue edges to blue edges. So here I've drawn sort of finitely many red and blue edges because it's a lot easier to draw. In practice, we'll often have infinitely many red edges and blue edges, but we still ask that we're going to ask that these isomorphisms sort of biject between the red and blue edges in that case. So how is this useful? So if we know this is true, and we want to extend the graph Tn in some way, maybe we could try and stick a subgraph behind one of the red edges. And so normally, if we did this, we might ruin the pairings that we had in the last stage. But if we stick the same graph behind all of the red edges, then because these pairings sort of maintained the red edges, the isomorphisms that mapped Tn take xi to Sn take yi will extend to these graphs in a very trivial way. Hopefully that's clear. And similarly, if we wanted to put a little graph, say GB, behind one of the blue edges, we could do that as long as we stuck the same graph behind all of the blue edges. And so in some way, this gives us sort of 2 degrees of freedom, which is going to be enough to build our bigger graphs which have this required property. Okay, so this is what the sort of general step looks like. We have our Tn and our Sn with these red and blue leaves, and we've got a vertex xn which lies in Tn. And so we want to build a graph in which xn has a pair. So first of all, we're going to need to find something, we're going to need to build something on the bottom here that looks a bit like Tn take xn when we remove a vertex. So perhaps a simple way to do that would be the following. We're going to pretend this graph Tn is rooted up at the top there on that red leaf. So here's the red leaf. And then we've got some tree hanging down here. So maybe it looks like this. And say here's xn. And so we could think of xn as sort of hanging off this tree by this edge which connects it up to the root. So one way to build another tree, which had a vertex which behaved like xn, would be to just pull this whole edge off and stick it on somewhere else. So we maybe draw a tree down here where we've sort of grabbed this leaf, edge, and we've just stuck it back on. So here's sort of maybe call this this one here, this yn. So hopefully it's clear that if we delete this vertex and if we delete this vertex, we get the same card there. And so in this picture here, I'm going to draw this down here. Imagine I've grabbed xn in the little triangle that it's connected to and just stuck it on the other side of this thing here. And so because we've got a lot of freedom with where we glue this edge back on, we can maybe do it in such a way that these two things are not isomorphic. So this rhombus thing is just going to represent some graph which is non-isomorphic to Tn, where yn, if you remove yn from this graph, you get the same as if you remove xn from this graph. Okay, so now we have something that looks like it could be a pair for xn eventually, but we need to make sure that it's a super tree of this graph Sn that we started with. So maybe we join them together by some path from this blue edge to this red edge, and this green and yellow edge will behave like the red and blue edge on the next stage of our construction, but that's not too important. Whereas I won't have time to fully describe that. So this is a good sort of first step, but now if we remove yn from here and xn from here, this graph looks quite different from this graph. So we might need to stick a copy of Sn onto x here. So this is our first approximation. And hopefully you can see here that if we remove xn from this big graph up here, and if we remove yn from this big graph down here, then we should get the same card. But this is not going to maintain the old pairings. And we know that because we know to maintain the old pairings, we need to stick the same graph on every red edge in Tn and Sn, and the same graph on every blue edge in Tn and Sn. But here we've just stuck this onto one red edge and this onto one blue edge. So to fix the old pairings, we could just stick, so here on the red edge we've stuck sort of yellow and green thing and the blue thing and this triangle. So maybe onto every red edge here we could stick this same little gadget. Similarly here onto this blue edge, we've got a rhombus and some edges, and so in order to maintain the old pairings, we would need to stick a copy of this graph onto all the blue edges. So this is a sort of a second approximation to our new graph, Tn plus 1 and Sn plus 1. And now, because we have the same graph on all the red and blue edges in Tn and Sn, this will preserve the old pairings. But because we stuck these things on here, we've now ruined the pairing between xn and yn. And how have we done that? Well, we wanted to sort of map this square to this rhombus, but now we've added all these graphs at the bottom of the square and none to the bottom of the rhombus, and similarly for the triangle. So to fix this, maybe we go back and we stick more graphs on here. But that ruins the old pairings again. And so we keep going back and forth, sort of countably often, until at the end we're going to get to some graph at the limit. And perhaps it's not immediately clear, but one can check that in fact both of these things are now going to be satisfied by this sort of limit object. broadly, this thing has sort of a tree structure where you have these red and these blue edges, and behind all of these red edges, the same graph appears. And so that guarantees that the old pairings are carried over, and then this new pairing maps this square to the rhombus, and then you can check that, well, through this red edge up here, we end up a triangle, and then the tree structure, which is like this, and all these things at the bottom are just these things at the bottom. So that's sort of the idea behind the method of building these new trees which preserve the old pairings, and then, yeah, via the proof method that I sort of sketched before, we eventually end up, after we've dealt with every single vertex, with this pair of non-isomorphic trees with the same card. Okay, I think that's all I've got time for, so thank you very much for your attention. So the question is, what happens with edge reconstruction? Edge reconstruction was also conjectured, I think, by Nash-Williams, but I can't remember. So I think we were sort of aware that the same method should deal with the edge reconstruction problem, and indeed you can just do a very similar construction. In fact, one of our co-authors, Peter Heinig, noticed just before we sent the paper off that in fact these two graphs we built were also non-edge reconstructible. It turns out a quirk of our construction, you can actually find some edges which play the same role as the vertices here. So in fact, it's quite interesting. The graphs we built, I think, are the only known example of graphs which are both non-vertex and non-edge. Oh, maybe that's not true. I don't know about that. But they're non-vertex and non-edge reconstructible simultaneously, which is quite a nice facet of them, I guess, and locally finite.